Hello. Today I would like to introduce you to my school project, how to compile it and make it running, also how to make use of the basic systems you can find in this project and which could help you with your projects. The source code is hosted on this address on a GitHub, and you can also find it in the video description down below. I will guide you through the whole process from the scratch. So first let's open a Git Kraken, which is a free Git repository management tool. First I will clone it to my workspace's directories here. I will copy the address from a GitHub. Let's make a name and clone the repository. This will take a while. Video magic. We just jump it over it. We can open it now. Now you need to set up all the submodules. It can be done automatically for you. This will also take a while. Let's just wait, or better, video magic. So magic happened, and we have all the submodules initialized already. And I will just quickly switch to another branch, because this is right now the head of my project. This will also take a while, but right now it is the simplest branch on which you can set the project up. In a few days it should be working in the same sense on the master branch. But right now, here's the cloned repository on a hard disk now, and I'm using Premake to manage this project. This is easiest way how to do it is from a command line. So you will just call premake 5 VS standing for Visual Studio, and the version you are currently using. I'm using the newest one, 2019. This should be pretty quick, and as you can see here, there's your solution generated on a hard disk. Let's run a compilation. This will take a while. As you can see, I'm compiling a lot of libraries beside of the engine code. So during compilation, let's just take a quick look over the projects you can see here in the Solution Explorer. First of all, there are dependencies. Those are libraries I'm using and compiling. I'm using some of them pre-compiled, as I'm still not able to compile them using Premake. This shouldn't be any problem for you. So the entry point for your application is over here in the Sandbox app. Right now it is pretty simple because most of the code is happening in the GL renderer. So here you are just opening a window you want to run and so on. I'm opening an experiment window. I think for now you don't have to care about what does it mean and why it's called like that. Also I'm opening a dummy window with DirectX 12, which is still just experimental feature, so you can disable it like that if you are annoyed by a second window opening all the time. How's the compilation running? Let's run it. And now, as you can see, it's running from scratch. That was the whole process of getting the engine up and running. You can see that it took under 4 minutes with all the explanation and so on. So it's not that hard as used to be. And now we can get to the explanation of individual systems you can use to ease your project development. The best way in my opinion, should be to explain how to define the level. You can define it outside of the code, mostly. Let's open our repository on hard disk, and you can see here a bin folder where all your executables lies. The main of them is here in sandbox, but if you would simply run it from here, it won't work, because working directory for the executable is right here in data folder. Here are all the data you need to run your repository, and here we can start with our explanation of how to define a level. If we open a levels folder, we can find there are two levels already defined here. One of them is called dark and the other one main. If we open a dark level, the level is defined as a simple XML file. The structure is obvious and you can just copy it from already existing levels. The level consists of a word where all the entities lives. The player entity is mandatory, and then you can define the other entities. I'm building a simple entity component system, and you can see it even from here. For example, there is the entity called floor, which has just one component, static mesh. The definition is pretty simple. You can omit most of the information. All you need is a file path, which contains a path to a obj file. The root for models is, as you can guess, here in the models. So if I open it, you can find here plain obj, which contains the plane you can see in the scene, and here you can even omit material. Then the basic one will be used. So if I will just delete this, you can see here that the floor turned to this odd color, which is probably defined in the basic shader. The basic shader is really using only the basic shading models you can imagine. Then for a static mesh you can define quite a few maps: color map, roughness map, and I'm also supporting normal mapping, so this is all you can see in this original scene right here. The other basic components you can find here are point light, which really just defines a point light with some translation against the original entity, and some color. The translation uses this universal format, and you can also see that this wall is also translated and rotated. Translation and rotation are only two transformations supported right now by the engine, so that's the place you can create an issue. And also static mesh can define a shadow pass shader, which would be used obviously during a shadow pass, but the plot twist is that there is no shadow pass right now in this scene. In the main level scene we can find another type of component called skybox, and also an example that each entity can have more than one component, but right now only one component of a given type is allowed per one entity. The last component supported by the engine is a skeletal mesh with the animation, but the usage of a component is too complicated. This is the very basic way how to define a level. Now another question is how to load it. To load the level, you need to go to a code. It's not in the GUI yet. And go to experiment window. And here is a setup word method. And the next very important thing is how to define a shader, which I can imagine could be the most useful feature for your project. Again, we need to go to a data folder, and here you can find the shaders folder. And to define a shader, you need to go through two steps. First step is to define XML file to define all pipelines steps. Here I'm defining the basic shaders, and the most basic pipeline consists just from a vertex shader and fragment shader in OpenGL. You can see it over there, and those paths, as you can imagine, leads again to shaders folder, which is a root for shaders. And here we can see a basic and vertex GLSL. If we go there, we can find the shader. And in this way you can define a shader for later use in the engine. From code's point of view, all you need to get your program and bind it to a pipeline is to get this singleton shader manager, ask it for your program. The string you are passing here is a name of a XML file. You can add the .xml or you can just omit it and then activate it through a shader manager. The shader class is defining most of the useful functionality of shaders, as setting uniforms, settings, UBOs, and so on. If we go here, you can see that you can upload most of the uniforms, you can bind samplers, and also bind uniform buffer objects, which should be the basic functionality you need to your project. There are quite a few useful tools you can use in this engine if you are using the shader management system I just showed you, and we can go through them quickly. As you can see, we are back to a basic shader. So here, if you open renderer and shader manager, you can see all the shaders used in your code. First tool, which speeded up my shader development a lot, is a live reload functionality. So let's open the fragment shader of a basic shader here on a floor and just assume that we would like to change something simple, making the floor darker. So here is a model color, and if I will just multiply it by 0.2, you can see that in the moment I saved the file, the engine just recompiled the shader and used it immediately. Besides of that, you can see in this shader quite a few preprocessor directives that are not part of a GLSL standard. First of them is include, and the include works literally how you know it from C++ or C. The only change is that the path is relative to your current file. So right here we are in the basic fragment GLSL. So if we go back and find the include folder, you can see there are frame constants, and all it does is just copy paste of the content of the file. Another directive you are maybe familiar with from C++ is define, and it also works literally how you know it from C++. Just define some name for it and then the value, and the value is just copy pasted everywhere. The other directives are those beginning with a @. Those are custom directives from the engine, and it stands for reflection types. So this struct is just a reflection of some C++ struct. So if we would go through code and open the area struct cpp, you would find there area light, and those are the members of this structure. If you are getting lost in all those directives, you can go back to the engine and you can find here output preprocessed. This is literally the same as you would use the C++ preprocessor to get the output of the preprocessed file. Another feature of this window is that if I click on any of the shaders, it would reload manually all the shader files. So just reload the basic, and now you can see here in the data folder a new folder called obj. So if we open the obj shaders basic and for example the fragment shader.o, it's literally the same file as this one, just after a preprocessor run. So here we can see all the finds have been deleted. Here is the content of a frame constants file, and if we go there, this is a area light structure which corresponds with the C++ definition. In this way, you should be able to rapidly develop your shaders using the live reload and include to reuse your code. You can find some utilities here in shaders folder, include some PBRT stuff, tracing for intersections and so on. Also the frame constants is UBO included everywhere to your shaders, which contains projection matrix, view matrix, pre-multiplied view projection matrix, camera position, sun position, and ambient light strength. Also a sun color. Most of the sun related things would disappear in the future releases. This should be a very fast way how to develop your shaders. Another useful thing you could do would be creating your own components. All the components have to derive from the I component and define some functions. But right now I can imagine the most of the components you would like to do are those that are renderable. So for those ones there is a iRenderable component which you can just inherit from, and all you need to do then is just define one virtual function. All renderable components right now lives here in a glrenderer / components. Let's take the simplest one, the static mesh, and just take a look what you need to do in order to be able to use them. First thing is inheritance from the renderable component, obviously, and then also a perform draw function. If we look into a perform draw, right now you can see that here I'm just checking for some things I need to do, then I'm binding all the textures, calling the commands regarding the shader, and then draw static mesh. Here in this function you've got your context bound, so you can call whatever OpenGL function you wish. Just be careful to call them, if possible, inside this lambda command, because all the commands are firstly collected and then committed as a batch. Beside of the lambda command, which is just hacky way how to try your OpenGL things, you can call different prepared commands. Another thing I can imagine you would like to do is to define some GUI in order to draw things. For example, if I will run the engine, the static mesh, which is for example the wall, has here GUI like that, and you can, for example, change the roughness of the surface. In order to do that, you can use already predefined elements inside the GUI namespace. You can find those elements here in GL render GUI. You can see that there are some input elements and also some output elements. You can use input or output elements as you wish in a debug draw GUI function. All you need to do inside the debug draw GUI is to create collapsible header if you wish to. It's not mandatory, and just draw all the components you want to draw. The window and so on would be set it up for you by the engine automatically. If you would like to deserialize your component from the XML definition, as you can see, for example here, the static mesh, you need to define another class, for example here, static mesh builder, which inherits from the component builder, and this simple interface have just one function called build, and here in the node parameter it will receive the XML node of your chosen component. So for example, I'm receiving here the whole XML element called static mesh. And how the engine knows that I would like to receive a mesh is by defining it here in a component builder factory.h. So if I would open GRenderer components, component builder, here is defined that when I will came across a static mesh, I will return the static mesh builder. I hope this is the enough info to start with this engine to write your simple project in it, and I hope you will enjoy working with this code base. So next time.